So the second lecture today is about Hyperledger. We are done with Ethereum, now moving on to another system. Or rather, Hyperledger is an umbrella. So it's managing entity as well. You can guess Hyperledger Consortium. After we have Bitcoin Foundation and Ethereum Foundation, we also have a Hyperledger Consortium. And the focus of Hyperledger is different, however. It's not cryptocurrencies. It's permissioned ledger on consortium network. Hyperledger also has an ecosystem of smart contracts, but it's totally different from smart contracts on Ethereum. The focus is on open source, and as mentioned, it's an umbrella. It's not one system. So there are many projects under the Hyperledger umbrella. Fabric is the flagship product. It's a permission DOT with proprietary consortium deployments. Another project is called Sawtooth. It's also permission DOT, but it has slightly different priorities. I'm going to talk about Sawtooth towards the end of the lecture. The third project is called Composer. It's more about smart contract language and development tool, but also how you combine different components to compose combine different components together in a single application. Cello is a framework for running blockchain as a service in the cloud. And R3 Corda is geared towards financial applications. So R3 Corda is a totally separate. Fabric, Sawtooth, and R3 Corda are in a way competing implementations of blockchain, even though they are within the same umbrella. So today we are mostly looking into Fabric, but we'll also briefly talk about Sawtooth. And the next lecture, I'm going to present Corda. Okay, so entities in Fabric. Entities are already quite different from those in Bitcoin and Ethereum. So let's take one step back. In Bitcoin, we have full nodes and lightweight nodes. And full nodes, they are part of the network, while lightweight nodes are not part of the network. In Fabric, we have peers, which constitute the network. So again, like there is a peer-to-peer network, similar to Bitcoin and Ethereum, but of course at a much smaller scale, because a typical proprietary deployment of Fabric would not have more than maybe 100 nodes, compared to a much larger scale of Ethereum and Bitcoin. To remind you, in Ethereum, we have over 1 million of validators only. In a typical Fabric deployment, we only have maybe an order of 100 peers. Then we have clients. Clients are representing applications built on top of Fabric. So clients are not part of the ledger, not part of the blockchain implementation in Fabric. Instead, they are building applications. They're the ones initiating transactions. Now, transactions in Fabric are usually not financial transfers. It's more like let's store this kind of data, or let's update the database. It's this kind of transactions. And finally, we have the order, which is a special entity in Fabric, or it could be a service, could be several servers which collectively act as an order. But conceptually, order is an entity which orders blocks and transactions. And it's separate from peers. Peers do not participate. Well, they contribute to the process, obviously. They send information to the orderer, but it's the orderer which decides on the order. So as you can see, it's quite different. And peers maintain the ledger. Clients do not do that. Orderer doesn't do that. Only the peers. More interesting concepts in Fabric. In Fabric, we have channels. What is a channel? Channel is like a representation of an application. So the same deployment can run multiple applications, or even within the same application, there could be multiple functionalities, and each functionality would have its own channel. So what's the semantic of a channel? A channel is like a partition of participants in the system. So in this example, you can see two channels. The first channel includes two clients and two peers, and the second channel includes two clients and two peers. So the channels can be overlapping, but obviously they are different. Now, what's the point of introducing those channels? Because each channel effectively maintains its own ledger. The communication is done on a per channel basis. The consensus can be done on a per channel basis. The storage of information and the updating all the databases, right? Like there is data world state, similar to what we've seen in Ethereum, but in Ethereum, there is just a single database storing everything that's going on in terms of the data on the ledger. In Fabric, you have the storage on a per channel basis. Another interesting principle that we have in Fabric is the plug and play principle. It's like, here we can see the standard blockchain reference architecture, which also play an important role in Fabric. And the whole idea is that Fabric provides implementation for each layer, right? But you can configure every aspect of every protocol. For example, you can use Kubernetes clusters. And then you can also re-implement any protocol. So what happens is that for every layer, Fabric has several pre-made implementations, and the administrator of the deployment could make a decision which of the several pre-made implementations to use for a given layer. And not only this, it's also possible not to use any of the pre-made implementations. Instead, you write your own implementation for a given layer. Or you take a pre-made implementation and extend it. And then, at the end, you get plug and play. So, which means that you can take out any implementation, any protocol out of the stack and put your own protocol instead. So it's highly configurable in that regard. It's probably the most configurable blockchain architecture in existence. However, there is a price attached to that. There is enormous amount of flexibility, but in order to exploit it, someone needs significant amount of knowledge, how to configure the system. So imagine IBM would be, Ethereum, Bitcoin, IOTA, Monero, you just download the executable as a client and you configure it, I don't know, within maybe half an hour or an hour, and then you start running. So it's totally feasible for a not so technically inclined person to use those cryptocurrencies. For Hyperledger, I would not dare to do it. Being a professor, I would still not dare to try to configure Hyperledger without someone's help. IBM gives courses 3 to 6 months on how to configure Hyperledger. So, and as a result, okay, so why is that? Because applications of Hyperledger are industrial strength. And the clients are coming from the clients, sending the entities of clients, sending transactions to the peers. They are coming from large organizations and companies and enterprises. And those enterprises, they hire dedicated deployment administrators for Hyperledger, whose entire job is to maintain the configuration of Hyperledger. So it's a totally different model. Some additional features of Hyperledger. There is no native currency because it's mostly not for cryptocurrencies. However, as always, there are some pre-made implementations of cryptocurrencies, and of course, which you can extend and make your own. So everything is possible in Fabric. But everything is possible means that someone needs to do it, or at least someone needs to configure it. There are a huge amount of libraries, of course, in Fabric, but even understanding the libraries takes some time. Another question is what kind of state tracking to provide. There are two principal approaches to state tracking. In Bitcoin, we use UTXO. In Ethereum and some other cryptocurrencies, we use accounts and balances. And there are advantages to each. So, for example, UTXO, operations on UTXO are easy to parallelize because operations on the balance, everything needs to be like streamlined or linearized. All accesses to the balance need to be sequential in order to prevent balance going into negatives. With UTXO, you don't have such a problem. If a user owns 5 UTXOs, each of the UTXOs can be processed and transferred in parallel. So UTXO approach is more parallelizable. It's probably also arguably better for anonymity, because the accounts are more difficult to make anonymous than UTXOs. On the other hand, if a user owns like 100 different UTXOs, then consolidating those UTXOs would require some large transactions, and accordingly the fees would be bigger. The transactions would be bigger in UTXO approach compared to the account approach. So there are also some interesting scalability issues with the UTXO approach. So the trade-off between the two approaches is not entirely clear. And in Hyperledger Fabric, well, you can guess it. You can do everything. You want to go UTXO, you can implement UTXO. You want to do accounts, you can use accounts. There are pre-made implementations and configurations, and there are recipes how to do things. Some interesting information about storage management in Fabric. So in particular, no state tracking is on by default. so that the administrator of the deployment needs to turn it on. It's impossible, of course, to employ one of the provided options. Now, the storage in Fabric consists of two elements. Well, three elements, effectively. There are blocks stored on disk, there's block index stored in a database, and there is a raw state, which is the actual state stored in a database, which can be CouchDB or a LevelDB, and there are advantages to each of the two. So that is also configurable. Now, a very interesting element of Fabric, which you don't get to see in other systems, is that blocks may actually include invalid transactions and yet be approved and become part of the ledger. So the ledger in Ethereum, in Fabric, it may include invalid transactions. Why is that? So why is it a good idea to include invalid transactions, and why is it okay to include invalid transactions? That's two separate questions. So what's the motivation for including invalid transactions? The motivation is that the order in Fabric needs to order transactions as fast as possible. So the order doesn't check the validity of transactions. I'll explain how validity of transactions is verified in Fabric. It is verified, but it's not verified by the orderer. So the orderer, whatever it gets, it just orders and puts groups into blocks and releases those blocks as fast as possible. So by not checking the validity, the orderer gets performance benefits. Now the other question, why is it okay? Why is it not okay for the other systems to have invalid transaction? Why is it okay for Fabric? Well, the difference, of course, is the trust model between permissioned and permissionless. In permissionless, if you allow invalid transactions, then there would be so many attacks and so many denial of service attacks. Everyone can get transactions, so the ledger would be in the permissionless blockchain would be totally polluted by invalid transactions if you let it happen. On the other hand, in Fabric, it's a closed environment run by industrial consortia. Okay, so usually they try to debug the programs and the contracts, the smart contracts in Fabric, sort of are usually more debugged before deployment. But there are also other reasons why transactions may become invalid. However, it doesn't happen too often. So the fraction of invalid transaction in a Fabric ledger is limited. So let's take a look at the processing flow. Again, you have a client, you have peers, and you have an orderer. However, peers are actually divided into several categories. You have an endorsing peer, and you have a committing peer. Okay, so it starts from client sending a transaction. To whom it sends the transaction? It sends the transaction to endorsing peers. So it needs to get an authorization. Every transaction in Fabric requires an authorization. From whom? Well, that's totally configurable, as everything in Fabric. So there is such a thing as endorsing policy. Endorsing policy dictates from whom the client needs to get an authorization. And an endorsing policy can be maybe 2 out of 3, or could be majority, could be anything, right? So the first check of validity for a transaction happens on endorsing peers. How do endorsing peers do that? Well, first of all, they see that it's a valid, like, authorized client who has the right to do this transaction. So there is access control, of course. But not only this. The endorsing peers would check which data would be affected by a given transaction. So they calculate what's called the RW sets, the read-write sets. The read set for a transaction is the list of data items which would be accessed for reading. And the write set is the list of data items which would be accessed for updating. And these two sets are produced by the endorsing peers, and they are sent back to the client, and also signed, of course. So the client should not be able to tamper. As the next step, client sends the endorsed transaction along with the RW sets to the orderer. Then the orderer maintains a pool of outstanding transactions. So it would create a block, and then it would send complete in block according to the block size and time limit and the other parameters. And then, okay, so to whom the block is sent? The block is sent to validating peers. And there are validating peers, usually it's the same, validating and committing peers. So validating peers finally execute the transaction. Please note that endorsing peers, they simulate the execution of transactions. They try to execute the transaction, but they do not update the actual data. They maintain a shadow copy of the data in order to simulate the transactions and produce their RW sets. It's the committing peers that actually execute the transaction, and they do it by comparing the RW set with the current state. Now, what may happen? So again, the first step of verification happens at endorsing peers. And at this point, the transaction may be valid. However, by the time the transaction gets ordered and sent to the committing peers, the transaction may become stale, invalid. That's one of the reasons why the transaction may become invalid. Because the state, like at some point in the past, the data was not updated, so the transaction was valid. In the meantime, the data got updated, and now the transaction cannot be applied any longer. That may happen. And it's the committing peers that would discover this situation. In this case, they would abort the transaction, but the block has already been produced by the order. Order doesn't get to rewrite the block in this case. And this is one of the reasons why invalid transaction may become part of the block in Fabric. Next, I'm going to talk a bit about the evolution of consensus protocols in Fabric, which are used by the orderer. The first version of Fabric used the PBFT protocol, which is one of the most common implementations of the BFT protocols. It's like it's a more complicated extension of Paxos. It was proposed in the 90s by professor from MIT, who later got the Turing Award, Barbara Liskov. Up until today, it's one of the commonly used BFT protocols with the open source implementation and so on. By version 2.0, PBFT was like not entirely replaced, so I should explain the progression. Each version of Fabric came up with the default and recommended implementation for the orderer. However, each version of the Fabric also maintains several alternative implementations. Like always, in Fabric, there are always alternative implementations for everything. So when Fabric 2.0 came out, the default implementation was using Apache Kafka. However, it was still okay to switch to PBFT. Now, Fabric version 3.0 came out with Raft as the default implementation. Raft is like it's a protocol similar to Paxos. It does not tolerate Byzantine failures. So why did the Fabric abandon Byzantine resistance between version 2.0 and 3.0? Because the applications, the clients of Hyperledger Fabric were complaining about the speed of transactions. And Raft is much, much faster than BFT protocols. Raft is considered, in practice, the fastest consensus protocol today, even though there is not much difference between Raft and Paxos in terms of the performance. But of course, by that time, it was still possible, so the default was Raft, but it was still possible to use PBFT. And in the latest version of Fabric, which is 4.0, they switched to what's called Smart BFT, yet another BFT protocol, which is an improvement over PBFT. So they finally, in version 4.0, they abandoned PBFT completely. And of course, being a non-Byzantine tolerant protocol, Raft tolerates a failure of up to half of the nodes, while Byzantine protocols tolerate failures of up to 1/3 of the nodes. Okay, what about performance? Fabric is the blockchain, one of the blockchains with the fastest, with the best performance in terms of both throughput and latency. So a typical throughput is in the order of thousands of transactions per second with 100 millisecond confirmation time. Yeah, I should mention, I should have mentioned earlier, perhaps it should be clear by now, but it's still worthwhile to mention it explicitly. So BFT, PBFT, Smart BFT, Raft, they are all deterministic consensus, final consensus. So again, what does it mean? It means that once confirmed, a transaction is never overwritten. So there is no rollback. And that's a difference from the probabilistic consensus in both Bitcoin and Ethereum and many other open cryptocurrencies. So 100 millisecond, order of 100 millisecond confirmation time. So that's quite good, but of course the exact numbers, I'm not giving you the exact numbers, I'm just giving you the order. Why? Because the exact numbers can vary a lot. They depend on a lot of factors. Okay, which factors? The version of Fabric, the version 3.0 is much faster because of Raft, but also the Smart BFT is faster compared to the earlier versions of BFT. It depends on the consensus protocol used. It depends on the relation between the input transaction rate and the block size. Right, so it has been shown that for a given block size, increasing the throughput rate, the transaction rate, the input transaction rate, improves the performance up to a certain degree, up to a certain point, and then there is a threshold. And if the input transaction rate exceeds the threshold, the performance sharply falls down, falls off. It also depends on whether we are running, or depends on the network, whether we are running Fabric in an optimal environment or in a more realistic deployment where failures may occur. And again, highly configurable, so there are numerous tweaks and optimizations, and they all exhibit different trade-offs in terms of the performance. So let's talk a bit about smarter contracts in Fabric. Smart contracts in Fabric, as I mentioned, are quite different from those in Ethereum. So there is no virtual machine in Fabric. Why? Because there is no need to standardize gas consumption, right? And another reason, okay, how do we make sure that the same transaction, when executed in different places, would reach the same result? That problem becomes that problem has been researched for many years. It's much more difficult in an open environment compared to a consortium environment. So effectively, Fabric does not resolve this question. It allows each program, each smart contract to run in a Docker container. And that's the default mode of execution in Fabric. So like the virtualization is different. I mentioned no use of gas. There is also no need for a dedicated programming language. Please recall that Solidity has several features which are very specific to the use of gas, for example. We know that, like the view keyword. View keyword means that the function is a getter and does not consume any gas. So there is no need for such dedicated language in Fabric. So in Fabric, contracts are supported in general purpose languages. Not all general purpose languages, but several general purpose languages. Another point that a smart contract in Ethereum must be verified on every node, or at least there must be sufficient number of validators. That's not the case in Fabric. In Fabric, a transaction and a contract not necessarily executed on all nodes. First of all, there is a channel, so it would only be executed within a given channel. But even within a given channel, not necessarily all participants in that channel would be running the contract. There could be a subset of validators. And another interesting point about contracts in Fabric is that they are managed in packages. So contracts in Ethereum are relatively small, as we saw. And each contract is more like a standalone unit. While contracts in Hyperledger are supposed to be full-fledged programs, they are much longer. So instead of talking about one contract, we are talking about package of contracts acting together as a single application. And therefore, smart contracts in Fabric are managed in packages. Those packages are called chain codes. And the advantage is that the configuration is given on a per chain code basis rather than on the per contract basis. So you configure packages instead of individual contracts, and that means less work for the deployment administrator and also for the programmer. Okay, the table here just pretty much summarizes what I said. Turing completeness. So Ethereum and Fabric provide both Turing completeness. Languages. So Ethereum supports several languages such as Viper, but Solidity is the most popular one. In Fabric, what are the popular languages for writing contracts in Fabric? Golang, Java, and Node.js, JavaScript. Who executes the contracts? So in Bitcoin it would be full nodes, in Ethereum it would be full nodes, in Hyperledger Fabric it's specified by endorsement policy, actually. So a subset of the endorsing peers and some of the committing peers. And the execution environment is a Docker container. So this table is quite big. It summarizes comparison between different blockchain platforms. So it's taken from this paper. So features, state tracking approach, Bitcoin UTXO, Ethereum account balance. In Hyperledger Fabric is application dependent. We are not considering IOTA yet because there would be a separate lecture on IOTA, I believe, tomorrow. The structure of data. In Bitcoin, sequence of block, sequence of block, sequence of block with transaction. Okay, here no difference. Maximum block size. In Bitcoin, it's 1 megabyte. In Ethereum, it's determined by the gas limit. In Fabric, it's configurable, as always. So different deployments will have different block sizes. On disk storage. So the ledger is stored as multiple files in all three systems. And state-related storage in Bitcoin UTXO set is stored in a LevelDB database. In Ethereum, there is very elaborate storage. And in Fabric, world state in LevelDB or CouchDB. And then additionally, there is block index in the LevelDB. In memory storage, it's also quite educational how they manage in memory storage. So in Bitcoin, the block index database is in memory, UTXO cache is in memory, and could be also Merkle tree of transactions. In Hyperledger Public, there is interest in management of peer cache, but otherwise, again, there are different mechanisms and it's application dependent. Okay, so that was about Fabric. Now, what can we say about Sawtooth, the other system? Sawtooth is yet another ledger. It's the second Hyperledger project to reach maturity. Well, by now, the other projects are also quite mature. It's also permissioned, mostly. It's also intended for consortium blockchain. So in what way is it different? There are several differences which are actually not very significant compared to Fabric. The first difference is that it's written partially in Python, and it also supports smart contracts in Python, because Fabric was pretty much against Python because of the performance, while Sawtooth saw it as a weakness because Python is a very popular language, so they saw the need to support it. Well, they support it, but as a result, of course, because they use Python, Sawtooth is noticeably slower than Fabric. However, there is something which it supports in terms of the performance, which Fabric does not, and that's parallel execution of transactions. So please recall that in Fabric, all transactions are serialized by the orderer. In Sawtooth, the consensus mechanism is different, and it allows for non-serialized parallel execution of transactions, with perhaps slightly reduced security guarantees, but better performance in that sense. So each transaction is executing slower because of Python, but together they may be better sort of parallelized, and therefore the collective execution may be faster. Sotov is one of those systems which uses proof of elapsed time based on a trusted execution environment. And that's another element. So trusted execution environment has benefits and also disadvantages. It's costly, right? So do we want to force everyone to buy trusted chips for the trusted execution environment? So in Sotov, you can do that. In Fabrica, they say resoundly no. There are also minor differences. So Fabric is purely permissioned, while Sotov can also run in some restricted permissionless environments. So they also have some technology to this extent. And that concludes the second lecture today.